Good morning, everyone. Today we're going to start with section 3.3. We're going to use exponential functions to help solve problems and really look at the setup that sets the foundation for exploring this newer idea of logarithms. So today is all about exponential functions. Specifically, you might recall this from Algebra 1. We have exponential growth and decay. So our standard form is f of x equals a times b to the power of x. Notice where the exponent is. It's in the variable is in the exponent. So what do we know? We know that the a value is your initial amount. The initial amount can never equal 0. The b stands for the base minus the growth factor. If b is larger than 0, then we're looking at exponential growth. If b is larger than 1, we're looking at exponential growth. If b is a fraction between 0 and 1, then we have decay. So when your b value ends up being less than 1, the quantity is decreasing as time goes on. If your b value is greater than 1, then we're looking at an exponential growth function. So that's what we're going to explore today is what does this growth factor have to do with how a quantity shrinks or grows over time. So really quick, if you'd like to pause this, because exponential function is a new type of function that we really want to focus on, here we have a function that every time period it's going to double. Some people might call this the doubling function. I'd like you to just pause the video and write down the domain, range, continuity, symmetry. Is it bounded, any asymptotes, y-intercept, and x-intercepts, just like we did from first trimester. All right, now that you had a chance to do that, let's go ahead and just check what we have. So domain. Remember, domain is all possible x values. Well, the way I think of it is any x value can be plugged in, and that will produce an output. So my domain is all real numbers from negative infinity to infinity. My range is referring to the outputs, the y values. Notice how every output is above the x-axis. That means every output is going to be greater than 0. So we could say from 0 to infinity is the range. The function is continuous on the entire domain. There are no breaks, jumps, discontinuities, anything that we have to be aware of. It's just a continuous curve growing. So it's continuous on the entire x domain. It is not symmetric. It is bounded below by the x-axis. So you could say bounded by the line y equals 0. Bounded below by line y equals 0. Well, that line y equals 0 is also your horizontal asymptote. We will never cross the line y equals 0. So you could even draw your dotted horizontal line in there for an asymptote. The y-intercept, where is the x value equal to 0? At 1. The x-intercept ties into the asymptote. Since we're never going to cross that value, there will not be an x-intercept. If you ever wanted to plot this without a calculator, you still could identify this. Pick a table. Plug in -2, plug in -1, plug in 0, 1, and 2. That actually helps us review some of the properties we talked about yesterday. So let me show you really quick what would happen if I plug in -2. So if I plug in -2, I get 2 to the -2nd power. Well, remember that -2nd power is the same as writing 1 over 2 squared or 1/4. Right? So that means I would go over -2, and this value would be up 1/4. Then you plug in -1. That's 2 over, that's 1 over 2 to the 1st power, which is 1/2. So go over 1 up 1/2. And then 0, that's the friendly one. Anything to the 0 power is 1, which is why our y-intercept is right here. And then 2 to the 1st power is just 2. and 2 squared is 4. You could keep going if you need to. You can always make a table for any values, but you can start to see the growth here. Each time you're multiplying the output by 2. All right, so what about this idea of exponential growth and decay? So we want to kind of look at a couple pieces here that we already know. We said the A value is like your initial amount. Well, if we're referring to population or a quantity of things, such as money, people, could be just a quantity that's growing or shrinking. A, or P sub 0, is the initial amount present at time 0. Think of that. If time was 0 and I put 0 in here, I'd have this whole thing to the 0 power, which is 1, which would give us the initial amount left over at time 0. Now, important vocabulary pieces. Notice how the B value is really broken up. The B value is your growth rate, that's going to be growth factor or decay factor, depending on the number. We think of it as 1 plus R. R is the actual rate itself. 1 plus R is what we call the growth decay or growth factor. And T represents time. So that might be a good thing to pause and just record this part down in your notes. We're going to be using these throughout the lesson today. So let's just work through a couple of problems here just to see how all of this is set up. All right, so initial factor, that's your A value or the P sub 0. That's the very first value here. You could always plug in 0 for the exponent. If I put a 0 here, that will make 1.2 to the 0 power 1, and it'll leave me with just 3. Now, the growth factor is the entire piece, 1.2. Notice, that's above 1. So because we have a growth factor greater than 1, that tells me that this function is going to be an exponential growth. So we know our quantity is growing because we're getting larger each time. The growth rate, the quick way to find the growth rate is to take the growth factor and say, well, where did that come from? That came from 1 plus the R value. So what if I just subtract 1 from both sides? I get 0.2. But what we want to do is we want to move this 2 spots to the right because our growth rate is mostly written as a percent. So we have a growth rate of 20%, which is the quantity is growing by 20% for each time period that goes on. All right, let's look at this one quick. Initial value. That's always the starting number, or if you plug x equals 0 in, that would get rid of this piece, turn it into 1, and we'd be left with the initial amount. The growth factor is what we called the B value originally. Notice this is less than 1, so this would be exponential decay. And then how do we find the growth rate? Well, same thing. We're going to do the growth factor, and that has to equal 1 plus R. So if I subtract 1 to both sides, I'm left with 0.002. And then remember, we got to write that as a decimal, or turn the decimal into a fraction, a percent. Ooh, that was tough. So we got 0.02%. All right. So why don't you guys try that for these 2 values, and I'll pause it and then show the answers. All right, so let's take a look at these. And actually, there's one thing I noticed here. I made a tiny error in terms of, so my growth rate on this problem up here was actually a negative value, because when I subtract 1, I get a negative value. The way we would talk about that in a word problem is we wouldn't say it's growing at a rate of negative 0.02%. We would say it's decaying at a rate of 0.02%. So we really don't need the negative if we mention it as a decay problem. So kind of the same thing over here. My initial value was 341. The rate, the growth factor, is 0.093, but it's actually a decay because this number is less than 1, which means we are growing at a rate of negative 90.7%, which means we're actually decreasing. We're taking away 90.7% of the quantity each time. So it's decaying pretty quickly. Here we have an initial value of 5.3. Growth factor is 1.013. That is a growth because this number, the b value, is greater than 1. And then when I subtract 1 from that, I'm left with 0.013, but we move this spot 2 spots to the right to get our decimal percentage, 1.3% growth. All right, so let's look at a couple problems. Your homework tonight is delta math. Do keep in mind that there's also a special formula out there called the Pert Formula. You might remember from Algebra 1. And we'll show you how to use that here really quickly. It's the same idea. So a person places an initial investment of $479 into account. So that's your initial amount, your principal. And then that's invested and earning an annual interest rate or an annual rate of 8.2%. We have to be very careful with this. This is the rate. However, you have to take that and turn it into a decimal. So you got to move this 1, 2 spots the other way to the left. And that will be the R value. And then why is this a base E? Well, it's because it's compounded continuously. So you might remember that from Algebra 2 or Algebra 1. Compounded continuously means the interest is always occurring. And that leaves us a special button in our calculator, which is a base E, which is around 2.718. So I'll show you where that is. So it says using the Pert formula, where V is the value of the account in T years, so we know T is based off of years, P is the principal initially invested, E is the base, the natural base, which is the natural log, and R is the rate of interest. Determine the amount of money to the nearest cent after 12 years. So right there, they tell us T is 12. So now we know everything about this function. The rest is just grab your calculator. So let's take our initial amount. We're going to leave E, and then we're going to put in our rate, and we're going to raise that, or times that by 12. Now keep in mind, this product is all in the exponent. So let's grab our calculator and we'll actually calculate that. All right, so we have our initial amount, and then I have to multiply that by the base E, and you can kind of see, it's really hard to see, but that blue e to the x, I'm going to go second ln, and that will activate base E. And then I recommend putting parentheses around this, but we have 0.082 times the 12, because that was the amount of, I think it was years. T was in 12 years. So how much money will be left in the account 12 years from now if we don't add any more money, but we are compounding interest continuously? And since this is officially dollars and cents, we're going to round this to the second decimal, so that would round that up to $1,281.39. All right, for our next problem, I'm actually going to come back to this slide, and we need to steal this equation here. Keep in mind, we know that P is the initial amount, R is the growth rate, and T is the time. So when they give us the Pert formula, we use exactly that. They'll most likely tell you to use that, or they'll say it's compounded continuously, so that's how you know to use that formula. Otherwise, if I have a problem like this, an element with a mass of 590 grams decays by 19.5% per minute. How much of the element is remaining after 15 minutes, round to the nearest tenth of a gram? So this formula we're going to take and use what we have known before. We can call it P of T if you'd like. So what we have is we have the initial P of T. P of 0 is the amount of grams present at the start. So that's 590. And then here's where it gets interesting. 1 plus R. Right? What is R? Well, R is our actual rate, but it says decay, and then we have to turn this into a decimal. So 0.0195 is my R, and the fact that it's negative means it's decaying. All right, so now, how much of the element is remaining after 15 minutes? T is 15. And then you can just grab your calculator, plug it in just like that. All right, so let's take a look. One thing you could do is you could actually add the 1 plus the rate first, and notice how that gives me a number less than 1. That's proof that we are decaying. And then the other notation thing is, remember function notation. If t is equal to 15, I'm going to plug it in here because this is saying the amount of the element remaining after 15 minutes. And then once we calculate the answer, P of 15 is equal to 439.1 grams. Notice we started with 590. If this answer was larger than that, that means I didn't account for that word decay, because I would be growing the amount of mass instead of decaying it or reducing it. All right, last piece here is, I'll give you a second to read through this. It's just on delta math, you have to fill in the drop boxes. So it's kind of interpreting the function, but there's a little bit of a trick. So it says the function is blank. Well, look at this right here. If our growth factor is less than 1, then we know this is a decay. And then the exponential rate is, we're going to take this value and we're going to say that to find the rate, we have to set it equal to the growth factor equal to 1 plus r, then we're going to subtract 1. And when we do that, notice how you get a negative answer. We get negative 0.003 is the rate. However, we want to write this as a percent. So this decimal has to move 2 spots to the right. And then we are going to say we are decaying, and then because we use the word decay, we don't put the negative in here, and we just write 0.03%. And then here's where it gets tricky. See the 24? So the 24 here is 24 times the amount of days. Well, let's think about that. But they want every value. It's not every day. It's every 24th of a day. Well, if you think of that, if I am timesing t by 24, to figure out what a single value of that would be, we're actually going to multiply that by the reciprocal. So if I do t is 1/24th of a day, well, wait a minute. There's 24 hours in a day. So that actually means that this is equivalent to 1/24th of a day is equivalent to an hour. So it might take a while to get used to just figuring out that units. Sometimes it can be tricky. All right, let's try one last one. So here you can see my factor is less than 1. My growth factor is less than 1, so it's a decay. Exponential rate, we're going to go ahead and do 0.95 is equal to 1 plus r. We'll subtract 1, and you get negative 0.05. But then we have to turn that into a percent. So I get 5%. It's not negative, or we don't put the negative because of the decay. Now notice, here we're dividing by 60th. So t is represented seconds. So I have a 60th of a second. Well, what I actually want to do is I want to kind of write that as an expression. If I have t over 60, if I actually take the value of t, which is a second, and I divide it into 60 seconds, then what I'm going to do is kind of think of it as a multiplier. I'll multiply by the reciprocal of 1/60th. So we're going to take 60 of a second, or if I do 60 of a second, well, 60 seconds is equal to every minute. So for every minute that goes in for t, we'll divide it, and that will give us that rate, or it'll give us the quantity that we're trying to reveal. All right, so work tonight, if you guys can do the pre-calculus 3.1 delta math. Remember, there are help videos built in, so if you get stuck, go ahead and take a look at that. Have a great day. Adios.